Hi guys, welcome to Astronomy 120. Today is Tuesday, September 20th. How are you guys doing? We have a lot of things to do today, tomorrow, good, and also on Thursday. So I just want to make sure that everybody is on board. By the time those who are not live in here, they will watch this recording, the time spent for doing these things, because I'll have to basically wait for it to be ready for me to upload. Furthermore, I have a class, actually after your class, I have a lab, I actually have to be on campus. I got off from that lab around 9 p.m., which means that I'm hoping for those who are not, of course, live with me, that the recording will hit them right around that time, maybe around 9, 10 p.m., at least on YouTube. So hopefully you guys will be able to also take advantage of what's going on. First of all, we have the lunar observation. The first lunar observation is due today, which means that you should have already planned and basically have a plan for what to do today. The instruction that you should have received yesterday tells you exactly what you're supposed to do, in that you go outside and you also look for the moon in the evening or later at night or early in the morning. So your job yesterday was to come up with a plan on how to go tonight. Basically tonight, it's not going to be much different than yesterday. So if your observation was around 9 p.m. yesterday, and you were successful to locate the moon and also find its shape, find its location in the sky. Again, what I'm asking for the location of the sky is not exact coordinates, basically just a rough direction. Is it to your south? Is it to your north? Is it to your east? Is it to your west? Is it right immediately in the zenith, or about immediately above the horizon, or somewhere in between, closer to the zenith or closer to the horizon? So you're going to locate the moon with this descriptives, not with the right ascension or declination or whatever other measurements that we used to use, the azimuth or altitude. No, just this description. Okay, you describe the shape of the moon. You also name the phase that it is in, and you also basically make a drawing. So that is basically the plan. So yesterday you should have planned, you know where to go, you know what time you're going to go. Tonight is your actual observation. I don't see a single cloud in the sky, so there's, at least if you are in the area where the campus is, you should not have any difficulty whatsoever to do your observations today. If you happen to be far away or traveling or something, and maybe there are clouds, your observation yesterday need to be basically safeguarded, because you still have tomorrow also to do your observations. In one of these 3 days, ultimately, you're going to be able to locate the moon. If all fails, make a guess what happened, okay? Is it, maybe it's potentially it's a new moon, so is it, okay? So that is basically for your lunar observation. It is extremely important. It goes toward your grade, so do not basically neglect that. That is item 1. Item 2 also that we have going right now, I need to do by tomorrow night, and that is the exam review. Some of you already did that, and they should have, at least the ones that I already have graded, they should have gotten full credit for doing that. Take advantage of it. It goes to your participation, but it also helps you prepare for the exam. So I'm hoping that you guys take advantage of that and also prepare seriously the exam, because the midterm is on Thursday. I know I already sent a couple of messages already regarding the midterm and the review and all of that, and I'm following up just to make sure that you guys are aware also of the importance of these things. The midterm itself carries a lot of weight. Usually midterms have a lot of weights. Exams have a lot of weights in the overall grade, which means that if your grade was not really, and you already have everything that needs to be graded has been graded up to this point. So you know if your grade is not what you expect, there is a very good chance you can make up a lot of grounds just by doing extremely well in the midterm. which means also the other way around. If you're a grade, you're satisfied, but you say, you know what, I'm good with it, so I don't care about it. That could also drag your grade down. So please be careful with that, because that is important. So take care of it, prepare for it seriously, and come to it. I only wish and hope to see everybody scoring the maximum possible, 100% in it. That's why I'm trying to get you guys to encourage you as much as possible, because I only be happy, honestly, if everybody gets an A in the class, okay? And I'm hoping that you guys are taking advantage of these things that are before you, okay? So this is the second thing. The midterm itself is actually on Thursday. It opens up in the morning. Because I'm teaching, I actually have a lab from 11 o'clock until like 2 p.m. So I'm not available during that time. And I also have another lab at 5:35 p.m. till 8:35, something like that. Given I have to drive back and forth, so there is a window in here that I will not be available for you to answer any of your concerns. As a matter of fact, after 5:30, I will not be able to answer anything. So if there is a problem, I'm hoping that the early ones who go in, take the midterm, then those problems would be resolved, okay? So that is basically the plan. We will not have a live session this coming Thursday. Again, just to accommodate those who already have allotted their time for the class, because you may be working, you may have other classes, and the only time you have available for an astronomy class is during the allotted time. So during that time, that is when you're expected then to take the midterm. However, it's open in the morning, so you could go and take it in the morning and do whatever you want to do with the rest of the day. Or if you're busy during the day, yes, Vanessa asked a very good question. Is the midterm available only on that day? Yes, absolutely, on Thursday, the 22nd, because I mean, I cannot honestly be answering questions on the midterm the next day or the day after or something like that. So it's only available on the 22nd. So you have to really take care of it on that day, because worst comes to worst, you have the allotted time that we agreed on from the beginning that I published in the syllabus. Now, if that doesn't work for you, and this is directed to those who are not here attending the class live, you still have the morning if you have work or classes in the evening, or if you have work or classes in the morning, you still have in the evening to take care of it. Sounds good, Vanessa and everybody else? Okay, very good. So this is very good. Thank you, Kara. Thank you, everybody. So the point being in here is that this is where we stand. So we have three things that are extremely important. First of all, the project, don't forget that. It's important, albeit it's not due until October, but you have to do the legwork today, starting from today. And then you have the review, which you still have time, honestly, to finish it and do it well, which ends by tomorrow evening. And then the midterm that is on Thursday. There is no class on Thursday. There is no Zoom session basically on Thursday. Now, which brings me to another point, to those who are sitting in my Astronomy 125, which is the lab version of this class. There will be lab on the 22nd. So the fact that you have an exam for Astronomy 120 doesn't excuse you not to attend the lab on that day. Make sense? I know some of you are not bothered with this one. Good. But the others who are sitting in that lab session, they need to be aware of this fact that we still have a lab on that day. Okay, that's actually an important lab too. Okay, so today we have units 37 and 38. They are not part of this exam. They are part of the midterm too. Okay, so that is the idea behind it. And what these two units are dealing with, they are dealing with the Earth. Okay, again, we're trying to build the little by little, basically our way toward the stars, toward the galaxies, toward the universe at the end of the day. But we start always by what is familiar. And this is actually an important skill that you actually can take to your workplace. If you're given with a task to solve, whether you're in a medical field or an engineering field or a book to write or something to do, okay, usually build your way from what is easy and then start to grow, start to basically make your way through it. Don't tackle the problem from the get-go, from the top, and then you will be lost. You don't know how to get going with it. So start with what is familiar to you and see if you can find a version of it to solve the next level issue, which brings you to a higher issue so that you basically overcome the entire problem. which is a skill that we learn in here also from this astronomy class. Because here is a question. We want to learn about the planets, actually we want to learn about the stars. But what is the most familiar planet amongst them? Of course, it's the Earth. So let's start with that. And that is the idea behind it. And then at the end, we're going to go to the moon. And then when we start learning about the stars, we go to the sun and so on and so forth. So that is the plan, okay? So let me share with you, and I'm going to try to make it as brief as we can today, because again, we want to get going with our reviews and things like that, and the other matters. So let me share Unit 37. So Unit 37 basically deals with the Earth again, okay? And its structure, and it's what's made up of, okay? And what we know about it, and how did we come to know about the Earth. Unit 38 deals with what is above the ground. So basically what Unit 37 deals with is from the ground below. So if you look at the Earth, you're going to look all the way down to the Earth, to the structure. Unit 38 looks from the ground above, the atmosphere, basically. So that is basically what we have. So what do we have on Earth? We have the following. Basically, we have its crust, the ground that you walk on, okay? But that's not the entire Earth. Actually, the Earth is mainly water. Its surface has a lot of water in it, okay? That is what is known as the hydrosphere, okay? So that is part of the structure of the water. So it has about 70% on its surface is water, and the other 30% or 29% to be more specific is what we usually refer to as the crust of the Earth. So you ask me how thick the crust of the Earth is. It's about 10 kilometers to about 70, 80 kilometers. 10 kilometers is actually near the surface of the, in the bottom of the oceans, okay? It's a thin layer before you get into the next layer, which is the mantle, okay? If you go to the Himalayas, for example, on top of the mountains, you have the entire mountain to come through, to overcome, and then you have the ground below it. So that's about 70, 80 kilometers. I mean, the mountains themselves, the highest mountain is about what, 8 kilometers, 9 kilometers, 8 point something kilometers. So it's nothing, the mountains, okay? As a matter of fact, in the textbook, it tells you, it references to if you take the entire Earth and basically reduce its size to an apple, the entire crust of the Earth is smaller than the skin of the apple. So it's a very, very thin thing. As a matter of fact, if you reduce its size to that size, it's smoother than the apple. Just to give you an idea how, I mean, we look at the mountains and the hills and we think that they're high and so on and so forth. But if you take the Earth and you reduce it to that size, it's actually smoother than a billiard ball. It's extremely smooth, okay? So it's not that high at all. So that is just to give you an analogy of the Earth, okay? Obviously, after the crust comes the mantle, I mentioned it, and that the mantle its temperature starts to increase the further you go down. And these two are made up mainly of silicon and oxygen combination, okay, in a silicate, which is what we know as the ground, which we know as the dirt, okay? So that is basically the two layers of the Earth. Then comes two more layers, and that is the core of the Earth. The outer core, which is kind of a liquid because it's extremely hot. And then the inner core, because of the tremendous pressure on it, it's actually a solid. So this is the structure of the Earth, okay? So let's get into a little bit more detail to see the Earth. Again, look at the different layers or the different depth, if you wish, of the surface of the Earth itself, okay? The surface of the Earth has the continents that we know them as the continents, but the continents are just if you wish a face to another thing, which are the plates, the plate tectonics that are formed on the Earth, okay? So this is basically what we know. The density of the Earth, namely, if you take an amount of the Earth, a liter of the Earth, a liter is roughly the size of a bottle, basically, of water. Okay, if you go and buy a little bit a large bottle, because some of the small ones, they're 500 milliliters, which is half a liter or a full liter of water. So if you take a liter of the Earth and you weigh it, on average, it weighs about 5.5 kilograms, 5.5 kilograms. But obviously, if you go outside and take the dirt out and put it in 1 liter of that, it's not going to be actually 5.5 kilograms. It's not going to be 5.5 kilograms. It's not going to be 11 pounds, basically. It's going to be less. It's going to be about 6 pounds. Okay. The reason being is, when we look at the density, we're looking at the entire density of the Earth, and it's easy to find, honestly. You don't have to weigh that. You don't have to do that. All you have to do is, what is the mass of the Earth? Okay, you're asking, how am I going to weigh the mass of the Earth? Well, there is techniques. One of them is, for example, how fast the moon goes around the Earth and how far it is from the Earth. From there, you apply Newton's laws of motion. You apply actually Kepler's third law. And instead of putting the sun, you put the Earth, because in this case, the body that revolves around the Earth. And now we find the mass of the Earth. Remember that Eratosthenes was able to find the circumference of the Earth, from which we can find the diameter. All we have to do is divide that number by pi. Now we have the diameter of the Earth, or its radius, if you wish, because half the diameter is the radius of the Earth. Then there is a geometry, there is a formula in it that gives me the volume of a sphere, which is, I mean, it sounds complicated, but it's just in number 4, which is 4 times pi, which is at 3.14 divided by 3. The whole thing is just a number in here. So, okay, 4 times pi divided by 3 is about what? 4 something, 5 something. So it's a number times the cube of that radius. So it's basically how, once you find the radius, you find the volume of a sphere. Now you have the volume of the Earth, you have the mass of the Earth, you divide the two, and now you have the density of the Earth. Okay. But if you look at the density of the surface of the Earth and you actually conduct an experiment, it's less. It's about 3 kilograms per liter. So that means that inside of the Earth must be made up of far more denser materials than 3 kilograms per liter. Of course, you need a reference in here. It's important to have a reference of what we're talking about in here. If you take a liter of water, twice the 500 milliliter bottles of water that you can grab from any store, Walmart, if you like. If you take 2 of those, that is 1 kilogram. 500 milliliter and 500 milliliter, or 1 full liter, is 1 kilogram, just to give you an idea, or about 2 pounds, slightly over 2 pounds. Okay. So that is the sense of the weight in here, because water's density is 1 kilogram per liter. There are materials that are denser than water. Case in point, for example, iron. Iron is about 7 times, almost 8 times more denser than the water. Because if you take a piece of iron and you put it in the water, it's going to sink. It must be denser. Aluminum is lighter actually than iron, but it's still denser. If you take a spoon made out of aluminum and you put it in a cup of water or in a bucket of water, it's going to sink. So this is what we talk about density in here. Air is less dense than the water. Air doesn't weigh as much for the same volume as the water does. That's why air floats up. Otherwise, the oceans will be upside down. Okay, the air will be underneath and the water will be floating upward. So that's not true. So this is what the density tells you. It tells you about the structure of something. And I'm just emphasizing on this point in here because you will see it somewhere else too for other planets. So when we talk about another planet, we try to see how dense it is. All we have to do is find a way to find its mass. Once we know its mass, once we know its volume, we have a density. Once we have the density of an object, then we start thinking about what makes it. Just by looking at the density. Earth turned out to be the densest object in the solar system, everything combined. Obviously, if you tell me, okay, if I look at the core of the sun or the core of Jupiter, they must be denser. What I'm talking about in here, the entire planet or the entire sun. The entire sun is less dense than the Earth. Earth is the densest object in the solar system. I mean, the large objects. I don't know about the small asteroids that are left over from the early formation of the solar system that are mainly iron or nickel. We're not talking about that. We're talking about large objects. Okay. The next one that comes after it is actually Mercury, 5.4. And then Venus. And so the inner planets, they're denser than the outer planets. There is more stuff in the same volume than the outer planets, meaning suggesting that the outer planets are made up of gas and maybe ice and things like that, but not like the inner planets that have rocks in them that are mainly a silicate of silicates and maybe iron and nickel and all of the heavy metals. Okay, so this is how we basically determine the density, and this is what the importance of the density is. How do we know all of these things? Of course, we use earthquake in terms of trying to find the different structure of the earth, the different layers I described earlier, the 4 of them. You use earthquakes to find it, okay? Just like, for example, when a woman is pregnant and she goes to the sonogram, what they use actually sound waves to go and penetrate and give you what's going on inside. That's a similar fashion, if you wish, except we have natural phenomena to help us with that. So it is in terms of the structure of the Earth. And this is a comparison between the entire Earth and the crust. So for example, iron on the crust, it represents only 6% of the crust. So all of the iron, all of the cars that are made up of iron and basically metal and steel and all of that, they're coming from this 6%. But there is about a third of the Earth is just plain iron. The entire Earth, whether crust or everything else. So where is most of the iron? It must be inside of the Earth. And you need this number to make up that number of 5.5 kilogram per liter, or 5.5 grams per cubic centimeter. It's the same thing. Now, oxygen on the opposite side, it's 45% or slightly almost half the content of all of the things in the crust and basically on Earth, at least in the upper Earth, but it only represents about a third of the Earth. Just between these two, you're looking at 62% of the entire Earth. The entire Earth, in addition to the silicon, now you're talking about mainly Earth. Add to them the magnesium, the rest of them is just a change. The rest of the materials are just changed. So if somebody is trying to understand what the Earth is made up of, they could safely say it's made up, the Earth is magnesium plus silicon plus oxygen plus iron and some basically junk stuff, okay? Because the rest of them, the nickel, the sulfur, calcium, aluminum, chromium, potassium, and even sodium, the salt, basically represent a tiny fraction compared to the rest of the others. So this is in terms of the overall composition and what is at the crust versus what is at the, so the silicon and the oxygen, they are mainly in the crust and they're mainly actually combined together in an oxide of silicon. So it's just some combination, and silicates they come in different kind of oxides of oxygen. So that's basically what this is looking at, and that's the dirt really. Okay, that's the ground that you go and dig in and plant your trees or whatever you want to do. Sodium again is on the Earth, and here it's mainly in the oceans actually, and also in the water and salt and all of the other things. Potassium also comes in a similar fashion as the salt too, and then chromium is another metal. Okay. That's mainly actually in the, as far as this one, it's really negligible. Calcium is what is basically, it's also in the rivers and near the waters, but it's also where bones are made up of and so on and so forth. Sulfur, which we think of as mainly basically on the surface, we think of it, a lot of it is on the surface, actually mainly in the inside, not on the surface, because on the surface, it's on the crust, it's only 0.03%, okay? Nickel is another metal. But look, these are just the part of the elements in the periodic table. You still have about some 90 elements in here because you deduct from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you still have about 80 other elements, part of the periodic table, that are a fraction of these things, okay? Fraction of these things, okay? So it's a lot smaller than this one. So this is basically in terms of the structure of the Earth and what it's made up of. And these numbers, they make up the 5.5 kilograms per liter perfectly. But again, how did we learn about these things? In terms of these layers, the different layers we were describing in the beginning, using seismic waves. If you happen to experience an earthquake, and if you have a luxury actually to be observant, because sometimes we panic during an earthquake and we lose sight of the fact that it's an event that's probably interesting on its own. If you don't panic, you will see that there are actually two kinds of waves that hit you. I actually was once basically on the floor laying around watching TV, and then I felt the ground actually moving underneath of me. And then for a moment, I was thinking, what's going on? Did something happen? I thought that I was imagining something. And then later on, the S wave came in. So the first one is the P wave, and then followed by the P wave, by the S wave. So the P wave is a compressional wave. If you have a slinky, I think we have some in the lab. If you have a slinky, what you do, you compress the slinky, and that compression will travel along the slinky. We call this type of waves compressional waves, because you take the slinky and you compress it from one end, and that disturbance actually travels along the path of the slinky itself. Or what you could do alternatively, you can move it up and down, and that motion up and down creates a disturbance that travels along the body of the slinky. So those are the two types. The first one is called actually a longitudinal wave. The longitudinal wave means that it's along the disturbance and the direction of travel are in the same direction. So in other words, this is what the disturbance is, but it's not localized. It moves from place to place to place to place throughout the medium. So this is a longitudinal wave, as opposed to a disturbance that goes up and down. Like, for example, if you take string and you create a disturbance by moving it up and down, yes, the disturbance is created in here, but that disturbance does not stay localized, it moves along the length of the string. So it's actually a transverse wave. Okay, waves are a phenomenon by itself, and we study them extensively, usually by themselves. Okay, sound happened to be a wave too. So what sound is, actually you're pressing against the air near your mouth as you're producing it, or a sound source like the TV, or for example, the computer, whatever it is. So it's compressing against the air. So what's going on in this case is that pressure, the change in the pressure that is traveling, not the air. The air moves in and out, that's it, but it goes back and forth, and it stays in that area. Unless you're blowing, of course, okay? And the air, and as it moves back and forth, the air next to the column, the next column of the air will move back and forth in response to the first part. And then the third portion of the air will move back and forth in response to the second one until it hits the receiver, which is in case your ear or something. That is actually compressional wave, similar to the P wave or the pressure waves described in this case. So sound is of a type P if you want to. It's a pressure wave. Light, on the other hand, is of this type S actually. So what's going on for light is there is an electric field and there is a magnetic field, and both of them are going left and right for the case of the magnetic field, for example, and for the electric field is going up and down, but both of them, as they are doing, they move in the direction in and out. So that is basically the distinction in here. So you have transverse wave, or the S wave, for the shear wave, basically what the shearing is. If you take a piece of paper and you pull it on one end, so it's going to create a tearing in it. But for the case of a medium like a slinky, it doesn't tear, it actually oscillates, goes up and down, okay? So those are the two types of waves. Well, here is the funny part of it, or the interesting part of it. Shearing does not do well in a medium like water, in liquid in general, because you try to disturb up and down, the wave dies immediately, it's attenuated, it goes immediately and stops. But the compressional wave in a liquid, like for example, the air is actually a fluid. So inside the fluid, you can compress on it and it moves. So that's how sound travels. You take advantage of it. So the P waves will go through the liquid, whereas the S waves will not. And that's exactly what we notice for earthquakes. So if there is an earthquake somewhere in here, and you have receivers that are all over the planet. So the first one, step of any kind of so you have seismographs everywhere on the planet, from different universities and government agencies and all kinds of things. They can actually, first of all, find the source where the earthquake started from, the location where it started, and the depth where it happened. Okay, so the earthquakes are just a way of the Earth to release its potential energy. That's all. There is a buildup of energy over time when layers start to move. And as they move, as they press against one another, they build up energy until they give up. So that's basically what the earthquake is. So in this case, you find where the source is, and you identify in the seismograph, you identify the two waves, okay? Where the first one came in, when the second one came in. Now, if you don't see the second one, if you don't see the S type of wave, that means that the wave must have gone through a liquid. It has been absorbed through that liquid. So the fact that you create shadows in here because of the S wave, then in this case, you can tell exactly that the Earth has a liquid in it and what is the depth of it. And not only that, depending on the speed with which the wave it reaches the other side, namely the P wave, you can find the density of that medium. So there are a lot of things you can learn. And that is how we learn about the Earth. Now, this technique is so powerful that we went actually to Mars, and we landed in a lander in 2017 called InSight. And that InSight, what it did was it dug about, I think, a meter in the ground of Mars, listening to Marsquakes, not earthquakes. They call them Marsquakes because they happen on Mars, just to learn about the structure of the planet. So we're still doing astronomy, we're not doing geology, but just to show you how powerful this technique is to let us know about the Earth. And we're trying to mimic it. We're trying to do something similar in other objects in the sky, like, for example, Mars. InSight, that one that landed in 2017, that is the plan for it. And it detected Marsquakes. It detected them, albeit different, I mean, slightly different in intensity, but it's giving us all kinds of information about the structure of Mars. So again, here are the different layers of the Earth itself. So again, we have a mantle, which is a very thin layer, and then, a crust, which is a very thin layer, followed by the mantle, which is a huge layer, then followed by two, basically, you have the outer core, which is a liquid core, and then you have the inner core. Because of the tremendous pressure, it's actually solid, and the temperature inside is so high that is equivalent, actually hotter than the surface of the sun. So that is basically what we know about the surface of the sun is about 5,800 Kelvin, but this one is about 6,500 Kelvin. That's comparable to the surface of the sun, okay? There is another process, because when the Earth basically formed, remember, a lot of those materials start to come together, losing potential energy and gaining, in this case, kinetic energy. Kinetic energy is a form of heat. So the Earth was hot. In that process, it's basically the denser materials go inside. It's like, for example, when you take a bunch of mixture, for example, and you try to sift through it. How they used to find gold, for example, in the old days when they go to the riverbed and they take some water, especially if they know that there is gold nuggets in there. So they take and they start sifting through it. So what happened in this case, the lighter materials will spread out, and the heavier materials and the denser materials like gold will go inward. So that is the process of differentiation in here, and that caused the more denser materials to go into the planet and the lighter ones to come out. So that's why that explains perfectly the structure of the Earth in here through that process. There is another source of heat for the Earth, though, and that is radioactivity. So the Earth, because of its huge size, still retains some of that heat, that ancient heat, from the relic heat, if you want to, from when it formed. But in addition to that, it's producing its own heat. And this is a very important point when we talk about other planets. We have to look at their size. For example, the moon is small. So it must have lost most of its heat from when it formed versus the Earth, which is bigger. And that is because the way you lose heat, depending on your surface area, okay? But also depending on the volume that you have in here, okay? So that is basically the condition for it, and how to lose heat. But the Earth now has far more heat to start with than what the case of the moon, which lost it for the most part. Furthermore, the moon, or Mars for that matter, do not have enough material to justify the continuation of the radioactivity for that long. In other words, most of the radioactive materials, they decayed and that's it. But the Earth, yeah, they decayed as much, but there still has more of them. So that's basically what the case of the Earth is, and the case of also what Venus is. But smaller bodies, like, for example, Mercury or Mars or the moon, they could not sustain that heat source for a long time. And that is critical because that explains something else later on, and that is the magnetic field. Okay. So again, one way for the Earth to lose its heat is trying to transfer it from the core to the surface. If you take, for example, if you go on the stove and take a pot, for example, and fill it with water, or your soup, for example, trying to heat it, you will notice that when the temperature starts to rise, that bubbles start to form. Okay, and the way that that's going on is basically what's going on. You have the heat source underneath, the furnace coming from the oven. Okay, that's heating the surface in here. So the liquid that is immediately in contact of it, its temperature is rising more than the liquid that is in contact of the air. So the liquid that is in contact of the air is less temperature, so it's denser in a sense because the density follows the temperature. The liquid is underneath, which is in contact with the source, is actually hotter and less dense. Because of its less dense, it rises. And the more dense one falls. And now circulation happens. We call this one convection. Okay. The same thing with the other side, actually it circulates in the opposite direction. So if this one is circulating clockwise, the other one circulates counterclockwise, and that has the bubbles start to form in here on your soup as you're heating it. Same thing for the Earth. So there is a convection also because there is a hot source. We described its temperature about 6,500 Kelvin. So again, those convections are responsible for the motion in the mantle, and that motion in the mantle will translate actually to the surface, to the crust itself. If you go, for example, in the surface, in the oceans, for example, you have those vents that open up, trying to get rid of that heat and actually dissipate heat in this form. Magma actually will flow upward, and in doing so, it's going to push the plates of the Earth toward one way or the other. And when it does, two plates can collide with one another, and one will go underneath the other, pushing the other one upward and the other one downward. That is a subduction. So that is another process also trying to get rid of energy, and this recycles the crust of the Earth. Okay, that is how the Earth actually is trying to take all of that carbon dioxide and all of these materials and basically recycle them through its surface. So the Earth is a dynamic picture. It doesn't look that much to us, but it's really going, albeit slow, but on a large scale, it's going very fast, actually changing its surface a lot. This actually leads to the plates that are forming in the Earth. So there are different plates, and this is the plate tectonics. If you take, for example, South America, and you put it next to Africa, they fit like a glove, actually. And you take the entire planet, and this is moving away or inward, depending on which direction this motion is causing the surface of the Earth. Now, is this something similar to other planets? This is something that we're trying to understand and learn more. Obviously, we need to learn more and more about this one. That's what astrophysicists and astronomers are doing nowadays, trying to understand what's going on with the other planets. We suspect, for example, for the case of Venus, that it's only one block. There are no plates on its surface. And that is way far. That's what one of its problems, trying to get rid of that excess heat underneath, but it's not releasing it as the Earth is doing in here nicely. Okay. And the only way for Venus to do it is go through those massive, basically, eruptions that go from every few hundred million years that cause all of that outgassing, basically, on the surface, that causes its surface to be basically unbreathable. I mean, with tremendous pressure on it right now. So this is something that is of interest to us. So if we're trying to find a planet, Earth 2.0, if you wish, it is important that we hope that we find at least places like this one, because that is actually a way for the planet to get rid of that excess energy, and in the same time actually also make it the conditions suitable for life. Okay. Again, this is basically how the Earth looked, and it's the plates and how they are moving, and they move around. And when they do, actually, they impact the entire atmosphere, the entire weather of the planet. If the entire surface, as it was at one point, all of it together in one place. So when it cools down at night, it does not release the heat as much, and this could lead to ice ages and all kinds of weather-related problems. Okay, so this is, and there are all kinds of evidence for this one. Okay, so this is today. This is 650 million years ago, and this is how the plates were moving millions of years around. Now, the point that I was talking earlier about the heat inside, and it's mainly nickel and iron, and both of them, they have magnetic properties. In other words, a metal, when it's heated and the Earth is spinning, that means that that metal is moving, and metal basically has free electrons. So what that does for you is it creates a magnetic field. So it is important to understand in here that you have two things. First of all, you need the hot source in the core, extremely hot, metal hot, not anything else, okay? And then you need a planet that moves at least fast enough so that you have electric currents inside of the core, and those create a magnetic field. And why do we talk about magnetic field? Because it's important. It protects the planets from cosmic rays and also from those deadly particles that come from the star, from the sun in this case, and protected by redirecting those charged particles toward the North Pole and the South Pole, creating what is known as the Aurora Borealis or Australis, depending if you are in the Northern Hemisphere or the Southern, the auroras in general, those light, the lights in the sky. But those are particles hitting the atmosphere at extremely high temperature, high speeds, and they come from the sun, and the magnetic field of the Earth, instead of hitting us in the planet, directs them to the North Pole or the South Pole, depending on their charge, if it's positive or negative, if they are electrons or protons. So that's basically what's going on in here. So it's a very important layer to protect Earth, to protect life on Earth, and that is the magnetic field of the Earth in general. For Venus, for example, it does not have a magnetic field to talk about at all. Why, you ask? Isn't it similar to the Earth? Doesn't have a core, solid core made out of also iron and nickel, similar structure, similar history, similar everything? Absolutely, you're right. But it is not spinning fast enough. The day on Venus is extremely long day. It's about 6 months, basically, Earth days. I mean, if you take the year and divide it by half, it's a long day. Actually, as a matter of fact, the day on Venus is longer than its year. Okay, so just to give you, so it's extremely slow motion. So yes, there are electrons, but they don't move fast enough to create currents to make significant magnetic field. Okay, how about Mars? Mars is spinning. The day on Mars is slightly over 24 hours, and the day on Earth is about 24 hours. So why not Mars? Well, in this case, Mars is not does not have a hot enough core inside to create a strong, meaningful magnetic field. So you see the ideal conditions for Earth in here. It has a core, hot enough, and also spinning fast enough to create a magnetic field. What's going on with the Jupiter? Yes, it has a core that is made up mainly of hydrogen in this case, metallic hydrogen. It's so much compressed that it became a metal, liquid metal actually, and it's spinning fast enough, actually spinning faster than the Earth. The day on Jupiter is about 10 hours. So it's spinning faster. So does Jupiter has a magnetic field? Of course it does. Not only a magnetic field, but it's a very strong magnetic field. So there is that correlation. Does Jupiter also experience auroras? Yes, and actually far more extreme than the Earth is. So that is really, but the radiation is mainly coming from different sources, like the Moon, Io, and other places. But the point in here is, you have what's going on in here. You have an understanding of the other planets and what's going on just by analyzing Earth. I mean, take a compass, for example, and you will see it going to point to the North Pole, indicating that the Earth has a magnetic field. Did the magnetic field retain its form all the way throughout? No, it reverses from time to time. The north goes south and flips down back and forth. And this is the geological evidence for it. Remember, those metals, they're impacted by the magnetic field of the Earth. They receive what is known as a magnetization. Those are the, for example, if you take a magnet rock, it has a magnetic field. Where did it get that field? It interacts with the Earth magnetic field. So sometimes the north is pointing one direction, sometimes in the other direction, indicating that the Earth is flipping its magnetic field left and right. Sounds good, guys? Can we go to the next unit? Or am I going too fast? Okay, thank you, Vanessa. Okay, very good. So let's go to the next unit. Let's share unit 38. Okay, we looked at the mantle, we looked at the crust, we looked at the core, the outer core and the inner core of the Earth. Now we're looking actually at its atmosphere. which is the next part of the Earth, okay? And that's from the surface up, not the surface down, okay? So that is basically the Earth, because we're going to be learning about other planets and things like that, and we would want to understand them, and we need that reference point, which is the Earth in this case, okay? Again, these are the objectives, so hopefully you guys are doing the reading, or not relying just on these lectures in here or the PowerPoint, so you're doing the actual reading, going through them and enjoying yourselves, okay? So the atmosphere is a very light structure. As a matter of fact, it's super thin, okay? It's negligible in front of the on center of the Earth, okay? And the Earth is mainly water, and the pressure is really can be understood with this analogy with the pillows. This pillow analogy is actually useful also for another planet that is mainly gas, like Jupiter, for example. Because if you take Jupiter and you put more stuff on it, it's going to shrink in size, actually, not grow. So the underneath layers, they exert more pressure, and that is the pressure. You are sitting right now, wherever you are, and you're moving lightly, and you think that, hey, I'm in a room and I can actually carry something. But if I ask you, can you carry a 10,000 kilogram truck, for example, 20-ton truck? You say no, but you are doing it right now because there is atmospheric pressure, which is about 100,000 newtons per square meter, or 100,000 Pascal. We call it an atmospheric pressure, 1 atmosphere. So the pressure is real, and it's something we experience on a daily basis. If you go to the swimming pool and you go about 10 meters below the surface of the water, you are actually under 1 atmospheric pressure, but not from the atmosphere coming from the water in this case, because the weight of the water above you. If you go 20 meters under the surface of the water, which is about what, 60 feet, at that point, you are twice at atmospheric pressure. You will feel a tremendous weight, not on your shoulders, everywhere. You feel like you're going to implode, especially if you're not wearing protective suit for it, okay? You're going to really feel that pressure. It's going to crush you from everywhere, and you probably cannot, of course, you cannot breathe if you don't have the, the equipment for it. But the point being in here, if you go 100 meters, at that point, the pressure is really, it's going to crush you for sure if you don't have the proper attack for it, because you're going to experience about 10 atmospheric pressure. That's still nothing. You have to go to 1,000 meters or 1 kilometer to experience what you would experience if you happen to be on Venus's surface. If you can live on Venus's surface, if you can stand on the surface of it, you will feel about 92 times the pressure of Earth. So this is something that we need to understand. If you happen to stand on the surface of Mars, and if you don't have the protective gears again, you're going to explode in that situation, because there is a lot less pressure than you're used to here on Earth. So far more pressure on Venus, far less pressure on Mars. But this is the atmospheric pressure that we were conditioned in and we lived through, and this is something that we recognize and live through. So again, the atmosphere of the Earth, where does it end? There is no limit, honestly, to it, because particles can go forever and ever and ever. So the density starts from 100% on the surface of the Earth, and it starts to decrease. If you're asking where are the planes fly, they fly in the troposphere, in the first layer, actually somewhere just slightly above the middle in here, okay? And then they have to be pressurized. Otherwise, you cannot basically live in those conditions, because the pressure drops, the density drops, okay? And this is the highest mountains in here. And this is basically where most of the clouds are forming, okay? Now, above the troposphere comes the stratosphere, okay? That is the second layer, and that is where the ozone layer is. So what is the ozone? It's the same thing that you breathe. It's an oxygen, with the exception of having 2 atoms of oxygen. You have 3 atoms of oxygen combining, and it's a critical for life on Earth. Without the ozone, the ultraviolet radiation will come straight through to the Earth and kill, basically, any living organism on the surface of the Earth. I mean, you'll be okay if you probably can swim under the water, but not on the surface of the Earth. It takes only a few minutes, and then everything will die, plants or animals, okay? So those are very, very powerful energetic rays, and we are being protected by this layer of ozone, okay? The temperature of the surface also starts to drop as you move up and up and up until you reach about -60 Kelvin, which is extremely cold, by the way. And 60 Kelvin, -60 Kelvin, there's no such a thing of -60 Kelvin, okay? I'm sorry. -60 degrees Celsius. Kelvin is always positive, but it can never have a negative number, sorry. So it's -60 degrees, -60 degrees, which is about -80 Fahrenheit. And then the temperature starts to rise now. So there's a lot of activity going on. To give you an idea, what the temperature is measuring is how fast the particles are moving, okay? That's all. So this number, sometimes when the density drops, there are other problems that you have to deal with, not the temperature. So the temperature, probably you're not gonna feel it, because what the temperature is, how fast is the air is hitting your skin. So when it's on a hot day, the air is moving faster than on a cold day, okay? But if there is not enough density to talk about, if there is not enough particles to hit your skin, you're not going to be feeling that. So that's basically in a nutshell. But if one of them hits you, it's going to hit you pretty bad. It's going to really hit you a lot. So that's what the density in here drops to almost zero, but it never really goes to zero. It's always there, okay? And again, this is how high you are, about 10 kilometers, just above the Himalayas. And then after that, it extends to about 50 kilometers, that is the stratosphere. And then after that comes the ionosphere, where all of the particles are basically ionized, okay? And this is where the Aurora Borealis form, okay? So the temperature in here, it's indicating that it's going to be very, very hot, and it is. So if a particle hits you, it's going to hit you with a very high velocity. That's what that means, okay? But remember, the density is extremely low at this point. You'll not be able to survive, I mean, the outside conditions due just to the pressure, okay, the lack of the pressure, that is, okay? So this is the different layers of the Earth. So the ionosphere extends above 80 kilometers and above, okay? And the ionosphere plays an important role in our telecommunications because it's made up of ions, basically. And what the ion is, an atom without one or more electrons. That's what an ion is. So in this case, when you send radio telecommunications, it bounces off because it acts like a mirror, actually, like a mirror. Okay, and that's why we use it for. We use it for long wavelength, basically, telecommunications, radio waves. Okay. So the auroras, I mentioned them actually from before when we were talking about the magnetic field. So this is how the magnetic field of the Earth would look like. And the reason why it looks this way is because the particles that are coming from the sun, in this case, are deformed in such a way. So if you are far away from the magnetic field now, far away from the Earth, I'm sorry, the magnetic field is kind of weak a little bit. And as you get closer and closer, it's going to be stronger and stronger. Now, as the particles hit the surface of the Earth, they're going to curl, follow the field line, the magnetic field line, and depending on their charge, if it's positive, they're going to fall in one direction, and if they're negative, they're going to fall in the opposite direction. That's why you have auroras on both the North Pole and the South Pole, okay? And also, when they do hit the atmosphere, they hit it with tremendous velocities, and they ionize that region that they hit it, okay? And that's what the light is. It's actually particles that are excited and trying to go back to their ground state. So when they go back to their ground state, they lose that energy in the form of light. That's what you see, okay? The regions that form in here of different kind of charged particles that are spiraling, they're called the Van Allen belt, and they have to do also with the type of particles. Are they electrons or are they protons? Those are the charged particles that follow the field line, the magnetic field line. So if the Earth did not really have a magnetic field, all of these fast-moving charged particles, they're going to also hit the Earth. So not only we need that ozone layer against the ultraviolet radiation. Ultraviolet radiation has no charge, so it's going to go straight through the magnetic field as if it doesn't care about it. So you need the ozone layer to protect us from that. Furthermore, you need the magnetic field to protect life also from charged particles that are coming from the sun, because the sun produces those with abundance, okay? Sun is mainly hydrogen, and hydrogen is nothing but protons with electrons. So when it expels materials, that's what we're going to have on the Earth, these two particles. So again, magnetic field is protecting them, in addition to the atmosphere also, which is actually plays a role on its own just to protect the Earth too. So that is why life is actually basically be being cocooned by all of these things to be basically safeguarded so that it can thrive on the planet. Okay. Planet like Venus, for example, has a super thick atmosphere. So these particles, they cannot actually penetrate because of the atmosphere. But the atmosphere is suffocating. It's mainly carbon dioxide and sulfuric acid. So there's no way you can survive that. In addition to the pressure, in addition to the temperature. So again, the issue of global warming is a real issue. There's scientific studies for behind it. And one of the problems that we use is the product that have chlorine in them, that are basically used for spraying and things like that. And when it goes to the atmosphere, it destroys the ozone layer. So it leaves us exposed to the ultraviolet radiation. And this is how the ozone, basically the openings in the ozone were documented. So this is not something that is to be taken lightly. Carbon dioxide, which is also a byproduct of the human activity, mainly through our factories and cars and things like that, also is a greenhouse effect gas, because then the radiation that comes from the Earth is absorbed by the atmosphere and goes through the atmosphere straight through because of their high frequency. But then when it hits the ground or the Earth in general, it's absorbed by the Earth and emitted back. When it's emitted in the infrared heat. And the infrared does not go past carbon dioxide or water for that matter in the atmosphere. It's actually bounced back. So now it's trapping that heat on the Earth. Similar to a phenomenon that you could do, please don't do the experiment. It's a very dangerous and deadly experiment. If you put a living organism, child or a dog or something in a car, and if you leave them negligently, you will be prosecuted, by the way. It's against the law, okay? And on a hot day, they will suffocate inside the car because of the car. Again, radiation is coming from the car. I mean, you can go yourself inside the car. If you lock the windows and you go inside the shopping and come back, it's a lot hotter inside than the outside. So you really have to let the windows down a little before you can actually sit in the car yourself. So again, what's going on in this case? Radiation from the sun is coming through the windows, going inside the car, heating the car seats and all of these things. And those, they get that energy through the form of all of the light that is going through. They want to get rid of it. So they want to dispose of it, just like your body tries to get rid of that excess heat. And then what it does is they don't sweat those things. I mean, we are a living organism that we have another advantage. But for them, they try to get rid of that excess heat by radiating it in the form of infrared, which is a longer wavelength, which is a different wavelength. The infrared, when it hits the window, it doesn't go through it. It bounces back. So it's trapped inside the car, causing the car to get hotter and hotter and hotter and hotter. So if there is a living organism inside, it could suffocate. And it's actually illegal to have that. But the point being in here is that is the same effect. That's what's going on with the Earth. The more we release carbon dioxide, the more water in the atmosphere, and the more we also destroy the ozone layer, the more radiation, first of all, is going to go through, including the deadly one, which is the ultraviolet. The X-rays, they come in the upper atmosphere and they're absorbed to Earth. So we're not worried about the X-rays. And for the most part, they don't go through the Earth. And also the gamma rays, forget about them. So the next ones in danger are actually the ultraviolet, and the ultraviolet are actually absorbed by the oxygen and the ozone, and they're actually going through the process of reforming the ozone. So that's why the ozone plays a critical role for the protection of the Earth. In addition to more carbon dioxide that is released, to more water that is released, to more all of these things, causing the Earth to heat up and causing actually life also to suffer. So again, these are the processes I was describing, the ultraviolet radiation. So when you see the UV, that's ultraviolet radiation. It's absorbed by the ozone layer and the oxygen actually too. And it's through this process that the recombination and combination of the oxygen with the molecule oxygen. So this is a molecule oxygen and this is an individual atom oxygen, and basically protecting when the Earth from this deadly one. So if you send materials with chlorine in the atmosphere, what they do in this case is that basically destroy part of that structure, causing the ultraviolet to basically more and more penetrate through the Earth and causing damage to the living organisms on the Earth just by virtue of this deadly radiation. That's part of the what the sun sends us on a regular basis. Okay, again, global warming is not political. It's not Democrat or Republican. This is a real thing. These are studies that have shown how the temperature has changed from the Industrial Revolution to today, and it's increasing with more and more human activity. okay? And this is carbon dioxide parts per million, okay? With time, as a function of time. This is in the early 2000s. So this data is actually scientific, not political, okay? I mean, would it have gone by itself? Yeah, it fluctuates up and down normally, but not on this curve, not following this curve, okay? So this is, basically when we trace it over millions of years and how the activity of life on planets and how it fluctuates up and down, as I was saying. There is another thing that we're going to talk about in here before we talk about the water cycle on the Earth and the effects of that on the Earth. And I mentioned that, I think, before when we were talking about the tilt of the Earth, the Milankovitch cycles, and those they have to do with two things. First of all, the tilt of the Earth, as I was saying, is not always pointing toward Polaris. It's actually pointing at some point to other planets, to other stars, okay? That's not the only thing. Also, the tilt itself is not always 23.5 degrees, changes as far as probably, what is it, 24.5 to about 22 or something like that. So sometimes the Earth will be aligned closer to its axis and sometimes more tilted. In other words, when it's more tilted, actually more extreme seasons. The hot gets hotter and the cold gets colder. Whereas it comes closer to the more regulated seasons, less rain, if you wish, less cold, less hot. So that is an effect on the Earth. There is another also part of the cycle is the eccentricity of the orbit of the Earth. Right now, the Earth can go as far as 153 million away from the sun to about 147 million kilometers away from the sun. But that eccentricity changes with time. Sometimes it goes further and then closer to the sun. So the further it gets, of course, the effects of that on the atmosphere also. And this is studied over millions of years. So that is actually part of the process that is, I mean, that can take, the Milankovitch cycles, they can take a few 100,000 years every time. And they affect the entire surface of the Earth in terms of weather. The tilt itself changing stars, that's about 26,000 years. And we saw that before. So again, the shaping of the Earth's surface is mainly water, as I was saying before. This is the Grand Canyon, and this entire surface of the Earth is actually subject to the flow of water on its surface, and the entire shift is basically impacted by that. Water on the surface of the Earth comes in three forms: liquid, solid, which is ice, and also in the form of gas, which is vapor, and all of that impacts the Earth in all of the forms, okay? The last point in here is the Coriolis Force, and this is something you could experiment with if you go and flush the toilet. You will always notice that the toilet will flush one way rather than the other in the northern hemisphere. In southern hemisphere, it should do the opposite. And also the bathtub, also when you unplug the thing so that you see where the water is. So why is that so? It's because of the dynamics of the Earth. The Earth is actually spinning on its axis, so the gases on its axis start to move one way or the other. And this impacts the weather. This impacts all of those basically formations in the weather and the motion of the air masses in the atmosphere, okay? So again, we learned a lot about the Earth. We're taking this knowledge with us when we move next time to other planets and try to ask similar questions and try to answer them to the best of what we know, try to see how much we can extrapolate this information to other planets, to other objects similar to it, to other objects that are not similar to it, because at some point we're going to be looking at structures that are completely different. So we're going to compare and contrast and see what we can learn and learn from the others. Obviously, others, they require their own investigation so that we can go and find more about them, okay? Okay, so these are the 2 units for this week. Again, we're not meeting this coming Thursday, a live session. So we're not going to do that. We're going to dedicate that day just for the exam. So if you guys have any questions, please let me know. I'll be more than happy to help you with it. Do the review. Make sure that you do all of the review to the best of your abilities. Don't forget tonight's lunar observation. This is your first outing. So you're going to go and do that. And I will see you live session a week from today. For those sitting in my Astronomy 125, which is the lab version of this class, if you are sitting in the section 1, we have a lab today, actually, at 5:30. If you're section 2, which is the normal one that some of you have been sitting on, that is actually the Thursday session. And your session on Thursday is actually section 2, not session 1. Sounds good, guys? Okay, very good. Thank you, guys. So I'm going to stop the recording. If you guys have any questions, please ask me. And if you want to meet also on a on a personal basis, whether online or in person, we're more than happy to accommodate that too. Thank you.